Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see basics of finite volume method. Okay, so we will in detailly see what is finite volume method, and we will contrast with the finite difference method. So, what is the major issues that we have seen in the finite difference method? So, we will try to sort it out using finite volume method, and what is the major differences and drawbacks and advantages. So, between the finite difference method and finite volume method, we will see it, and how do we apply for different types of grids we have. So we have the structured grid, we have unstructured grid. So for unstructured grid, can we use finite volume method, or for structured grids, can we use finite volume method? So if we compare like finite difference and finite volume method for these two grids, and with the finite difference method, so how advantageous it is, we will see in detail in today's model. Okay. So before that, we have to see the revision of the grids actually. So already we have seen in the previous module about grid or mesh. So basically, mesh or a grid is an entity where we will divide the domain. So basically, the square what I have drawn is basically it is a domain actually. So the domain will be divided into subdomains. So the outer edges. So basically, we call it as the boundaries of the domain. So the lines. So the x lines and the y lines. So basically, these two lines are dividing the domain into subdomains. So you can see number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 subdomains actually. So initially we had only one domain. So when we have drawn those grid lines, so x grid lines and y grid lines, so we have divided the whole domain into subdomains actually. So when we divide into subdomains, so what happens actually? So whatever the fluid which is entering, so that will be calculated in each and every segment of the domain. So 1, 2, 3, 4, so and so on till 16. So the how the fluid is entering, how the fluid is leaving the subdomain is very important. So when we see the smallest part of this basic entity is SL. Okay, so here you can see this is SL. So for this cell, so in the finite difference method, so what we have seen, so we have seen that so the corner or the edges, so basically these things are called grid points. Okay, so previously in the finite difference method, so we have actually derived or like let's say we have written the discretized form of equations at these locations actually at the grid points. So we have given index notation I, we have given index notation J, so we have given I, J and K. So we have given these index notations, and we have performed the discretization using finite difference method, which is derived from Taylor series of expansion. Okay, so that is what we have done in the finite difference method. Now in the finite volume method, so the majority thing what we see is at the center of the cell or the centroid of the cell. So here we can take this as cell number 6. Okay, so for the cell number 6, so what are the adjacent cells we have? So we have 7 actually. So cell number 7, and we have on the top we have 2. Okay, on the side we have 5. Okay, and the bottom let's say we have it as 10. Okay, so if we take cell number 6, so for the 6 there are 4 adjacent cells. Okay, so for those 4 adjacent cells, so we have to locate what is the centroid of the cell. So we take cell 2, 5, 7, 10. So for this 5 like 2, 5, 7, 10, for these cells, so we need to actually mark the centroid. So when we mark the centroid, so whatever the things we need to calculate will be actually depending on the location. So it will reach to the cell 6. So this, let's say this is the centroid of cell 6. This is the centroid of the cell 7. This is the centroid of cell 2. This is the centroid of cell 5. This is the centroid of cell 10. Now when we are calculating the values of flow variable, so these variables are basically taken the average of cells. So this one, these cell faces. So when you take this average, so at this location, so at the cell 5, so at the cell 5, what is the pressure, what is the velocity, what is the temperature, so will be calculated by doing some the average of the phases which are present on the corresponding cells. So let's say, let us take cell 5 actually. For the cell 5, so we have, this is the centroid. So whatever the values that we have on this phase and this phase and these phases and these phases, we do average by interpolating actually. So when we do average, so we get the corresponding value at the center of the cell. So this value will be taken as an input for the cell 5. So similarly, so let's say value at cell 5, next value at cell 6, we have to be found actually. Value at cell 7, value at cell 10, value at cell 2. So these values actually are very very important to govern what is the value at cell 6 actually. Okay, so how do we do it? So we will draw an imaginary, let's say if we take 1D, so let us take it as 1D. So for the 1D, so let us take, these are the boundary points. Okay, so this is the point of interest P actually. Fine. So these are the neighboring cells. So let us draw. So this is an imaginary neighboring cells. So this one we will locate is as west. So this is another neighboring cell. So this one we will locate as east actually. Okay. So what we are doing actually, so we are basically locating the point of interest, or let's say the node of interest, and so we are actually depending on the neighboring points. Fine. So here we have west, we have east. Why? Because we are taking 1D. So when you take the one dimensional flow, where the flow properties, let's say pressure and temperature and velocity and density, so these values will vary only with respect to x direction. So pressure P of x, comma temperature T of x, comma velocity V of x, comma density rho of x. Okay, so when we say the flow is one dimensional, so the flow properties, so pressure, temperature, velocity, density, so these values will vary only with respect to x direction. Fine. So when you say the flow is 2D, so the pressure will vary both along x and y direction, temperature will vary both along x and y direction, pressure will vary both along x and y direction, density will vary both along x and y direction. Fine. Now when we take this thing, okay, so this 1D, now we have located what is the point of interest P. So for this point of interest P, we require neighboring cells. So we have drawn that as west cell and we have drawn it as east cell. So why? Because when we are doing, so we require the neighboring cells. So since it is 1D, so we are seeing west and let's say east. Fine. So now this is for 1D. When we do it for 2D, so what we do actually, so again we will draw the area of interest, or the point of interest P. So here we are drawing the west. Okay, again we are drawing this east. Okay. Now for the 2D, so we have it as north and bottom, so we have it as south. Okay, sorry, we have it as south. This is for 2D. Now basically what is the major difference that we have seen? So we have seen, so basically in the one dimensional, so the point of interest P is depending on the neighboring cells, so which is of west cell and the other one is east cell. Now here in the two dimensional thing, so what is happening? So we are depending on the west cell, we are depending on the east cell. Additionally, we have north and we have south. Okay, so this is the difference between 2D and 1D. So here what is happening? So the pressure will depend on x comma y. Why? Because in the one dimensional we have only variation along x. The two dimensional we will have both variation along x and y, comma. So temperature both along x and y. Next, velocity both along x and y. Density both along x and y. So here what is the thing we are seeing? So one dimensional, two dimensional, the majority differences what we see is, so the flow properties so will vary only along x direction for the one dimensional. For the two dimensional it will vary both along x and y direction. So we say there is one more special category called quasi one dimensional flow. Okay, so when we say 1D, so what is happening? So here you can see in the diagram, so the area, so you can see correspondingly at different cross sections, so the area is also constant actually. So the area of cross section of the rod, or let's say the beam or the element along its length is constant. Okay, so that is called 1D flow. When we say quasi 1D flow, so the meaning of quasi 1D flow is the area also changes with respect to x direction. Okay, so that is the major difference that we need to notice. So when I say 1D flow, only pure 1D flow, here additionally with the flow variables, the area remains constant. So you take the beam element or the bar element, so whatever element you take, so the area remains constant. Now, when I say quasi 1D flow, what is happening? For the quasi 1D flow, here the area also changes. So let us take this. So convergent divergent section. So here area changes with respect to x direction. So you take this cross section, you take this cross section, you take this cross section. At each and every cross section, the area is changing. Fine. So that is what we need to notice for quasi 1D. So simple 1D, the area does not change. Okay, so when you take 2D, so area changes with respect to both along x and y direction. So if we have like a convergent divergent section or any other we have truncated, or let's say any other section, grooved section, so you take any elements like area, we cannot assure that it is changing. So here additionally we can write a comma x comma y. So area also changes with respect to x comma y direction. Fine. Now when we take it as 3D, so let us take it as 3D. So here we actually have to see in the form of cuboid. So basically there is a terminology in CFD. So when you have cell which has four sides, so we call it as quad cells. Okay, so instead of rectangle or square, what we say it as quad. So when we have the triangular unit, okay, so we say it as tri. Okay, and when it is projected to 3D, so this is the 2D cell, 2D smallest cell. So this one will appear for the structured mesh and this one will appear for the unstructured mesh. Okay, so if you take the structured mesh, the 3D entity, so we call this one as what? Hexahedra. So we call it as hexahedral cells. Okay, so now when we take this one, so in terms of prism actually, so this is called tetrahedra. Tetrahedra. This is hexahedra. This is tetrahedra. So here you can see that the two-dimensional entity for the structured mesh so is a regular entity. So we call it as hexahedra, and for the two-dimensional entity for the unstructured mesh, so we call it as the tetrahedra. Fine. Now when we are doing this finite volume method, so let us take the hexahedra cell to first mark it. So how do we see for the point of interest for the three-dimensional one? So we draw a cube. Okay, so we draw a cube. For this cube, so we will locate, this is a point of interest P. So this is what we have for the finite volume method in 3D. Similarly, so here what we have to see is, so we have we have to imagine it, we have another cube on the north or the top. Okay, and here there is one more node which is called east. So sorry, this is west. So here we have it as east. Okay, so similarly bottom we have south. Now additionally what we have, so we have here it as front, here we have backlets. So that is the difference. So you take it for the 1D. So for the 1D what we have, so we have point of interest P. For the point of interest P, so we have taken the west which is of the left side, and we have taken east which is on the right side. So with these two neighboring nodes of east and west, so we will calculate the values at the point of interest P. That is one thing. Next, in the two-dimensional flow, so we will take again the point of interest P. So with the neighboring points of let's say west, east, north and south, so we will estimate what is the value of the point of interest P. Okay, now in the 3D, so what is happening, so the point of interest P, it is calculated using west node, using east node, using north, using south, front, back. So in the one dimensional flow, so what we have seen, so for the 1D flow, P is depending, point P is depending on west and east. Okay, so let's say it is depending on two variables. For the 2D flow, what is happening? Point of interest P is depending on west, east, north and south. Okay, so west and east, and additionally we have north and south for the two-dimensional flow. For 3D flow, the point of interest P is depending on west, east, north, south, front, back. So what do we have here? So we have here two variables, like two dependent variables. Here we have four dependent variables. So here we have six dependent variables. So 2, 4, 6. So basically when we take 1D, 2D, 3D, so the major differences what we find is, so when you take the point of interest P, it is depending additionally for the four variables when you compare with 1D, and additionally with the two variables when you compare with 2D. Okay, now what do we do? So again let us take the variables. So for the variables P, pressure x comma y comma z, so it is depending on x comma y comma z. Okay, now temperature depends on x comma y comma z. Okay, and similarly what do we have? So we have velocity, it depends on x comma y comma z. So density, it depends on x comma y comma z. Okay, so this is how basically the approach for 1D, 2D, 3D will vary. And now in the finite volume method, so we have seen so how to calculate the values at the point of interest P for 1D flow, for 2D flow, and for the 3D flow. Okay, so let us take one small example. So we will see the diffusion equation actually. So we'll take the diffusion equation. So what we have, so we will actually take d by dx of, let us take this as mu. Okay, so mu of d by dx of, let's say, d by dx of u, let's take 0. So this is the diffusion equation which we have. Okay, so here the mu, let us take it as the viscosity. So there are two types of viscosity which we have. So we have one is called viscosity or dynamic viscosity or molecular viscosity, where it remains constant. So mu is constant with respect to flow when we take the flow does not have that much amount of turbulent intensity. Okay, now this thing, the mu will not remain constant when the flow turbulence will change from one segment to other segment. So let us take a pipe. For the pipe, so when we have flow, so when you have the eddies, more amount of eddies. So eddies are nothing but a recirculatory zones. So if you have more amount of eddies, and these eddies actually will make the wall or the flow near to the boundary. So very like having the dissipation of heat, it makes it actually. So these eddies, they will take the energy from the mean flow. So this is called the mean region. So from the mean region, so you take the wall and other wall. So velocity at the wall, this one will be 0, and this wall it will be 0. At the mean, it will have high amount of energy. So these eddies will get fed up with the mean energy. They take the energy from the mean flow, and the largest eddy will give energy to the smallest eddy. Let's say it feeds, okay, energy to the smallest eddy. So this smallest eddy will actually dissipate the heat at wall region. Fine. So at the wall, the energy is dissipated, which is the small eddy gets damped out. Damped out in the sense, first from the mean flow, the large eddy will take energy. This large eddy will supply the energy to the smallest eddy. This smallest eddy actually dissipate or let's say get damped, or it goes into other form, the form of energy at the wall. So the wall temperature or the properties at the wall will change. Okay, so that is why we have seen this eddy. So basically we call it as turbulent viscosity, so which is called mu T. So which is not constant actually, which is not equal to constant. So that is the difference which we need to see. So in the diffusion equation, so we have two things. One is the let's say laminar viscosity. You can take it other one as a turbulent viscosity. So total viscosity will be combination of laminar and turbulent actually. Now when you take the turbulent viscosity, so what happens at each and every section, here you see at each and every section the viscosity will not actually be constant. It varies with respect to space. Fine. So that is why we take mu T as variable. It is not constant. Fine. Now what is happening actually? So when you take this d by dx of mu, d by dx of u. So when we want to apply this finite volume method, so what we take? So we draw. So since it is 1D, so we draw point of interest P. For the point of interest P, so we draw. So what is the west node? Again, we will draw what is the east node. So for the point of interest P, we will draw what is west node and what is east node. So we will actually get the values of velocity, u velocity, at the value of P, at the value of W, at the value of E. But we don't know what is the value at the face. Okay, sorry, it's vice versa. So we know what are the values at the face, but we don't know what is the values at this grid point. Okay, why? Because at the phases the values will be known. So we have two entity which is called staggered grid, unstaggered grid, collocated grid. So where the values, where do we store the flow variables, that we will actually find it out. So there are two entities. So if we take it as x, y, let us take it as grid. So let us take this as centroid. So here along grid points, so let us take the velocities are storing. So u velocity, v velocity values are storing at the grid points. At the faces, the pressure value is storing. Okay, so the way of storing the values of flow variable at different locations, so will be actually it is a staggered, and there is one more entity called unstaggered and collocated, so which we will see in the further modules. But here we will actually see for a time being. So let us see that the values of flow variable are stored at the cell faces. So like viscosity, like pressure, so these values are getting stored at the cell faces. Okay, now what do we do actually? So in order to calculate so values at this west node and this values at the point P, so what we do is like the value at this phase A, the value at the phase B. Okay, so we will take, so mu at A is equal to, so mu at west node plus mu at point of interest P by 2. So this is what we have at the face. Okay, so this is one thing. Next, mu at B, phase B, will be, so mu at point of interest P and mu at east node by 2. So this is what we have. Now what we have done actually, so we have taken the average at the east node, average at the west node to get the value of the flux at the faces. Okay, so this is one of the approach. So this is a simple direct average what we are doing it for 1D. So let us take it as 2D, so 3D and 4D. Some other interpolation techniques are required. So you cannot take directly average. Let's say you have weighted function. So what we have, so let us take in some terminology. So let us take this is east node. Somewhere here you point P you have. So this is, let's say, east node. So here if you see, so what is the weightage of this cell? What is the weightage of this cell? What is the weightage of this cell? So mu at A will be actually weight function at A. So let's see. So weighted function at cell west into mu of W plus mu P into weighted function of P divided by, so weighted function of W plus weighted function of P. So this is one terminology. Okay, so we cannot directly take the value average for all the cases. So for some cases, let's say we have the points which are located at equal intervals. So for the first example, we have seen the point of interest P is located on the west side at the equal half, and at the east side, so the point of interest P is located in the middle. So that's why I have taken average. But in some cells, Not all cells will have same equal distribution of the faces with respect to this one. We need to add the weighted functions. So that is why we have seen here the weighted functions to calculate mu of A. And similarly, the weighted function for the mu of B, it will be, so WB, fine, which is of mu of B, plus next WP mu of P. This is WE mu of E divided by W of E plus W of P. So this is what we have. Fine. So in this way, we will calculate or we will estimate the values of the viscosity. Now, so what we have seen, d by dx of, let's say we have taken mu. Fine. Now next d by dx of u. Okay. So this is what we have is equal to 0. We have taken it as 1D diffusion equation. Now what we have to do? So we have to do one line integral actually. Fine. For the finite volume method, what we have is we will actually integrate. If it is 1D, we will integrate with the line. So if it is 2D, we will integrate with respect to area integral. If it is 3D, we will integrate with respect to volume integral. Okay, so that is what we have. So when we see the line integral, so we will have the limits in between, let's say the point, the west node to the east node. Okay, or in this between, what we do, so we will take this as, let's say, from west to P, so which is of d by dx of mu into d by dx of u, which is equal to 0. Okay, so this will be in between W and P. So the other one is, so what we have from P to E, so d by dx of mu and d by dx of u equal to 0. So we have taken the splitting mechanism in between west and east. So where from, let's say, from west node to point P. So this is one form of line integral you can take. Another thing, so from point P to east node. So this segment is for this formulation. This segment is for this formulation. Okay, so in this way we will divide in the line integral form for the finite volume method. So for the finite difference method, if you see, so what we have done, we took the grid point. At the grid point, we have taken the Taylor series of expansion. For the Taylor series of expansion, we will actually neglect some terms. So here there is nothing like neglecting the terms. So whatever the terms we have, we are doing the volume or the line integral or the area integral things, and we will do. Okay, so this is the basic insights of finite volume method. So in the next module, so we will see in detail, so how the west node, east node, and north node, south node, top or front or back, so these nodes, how do we actually write down in terms of formulation. So we will see the in detail formulation for the diffusion equation. For those diffusion equation, so we will elaborate it with one example problem. We will do it. We will solve it using some matrix terminology. How do we arrange the equations? How do we solve those equations? We will see using one tutorial problem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.